Greetings and welcome to my new calculus channel. My name is John Gabriel, and if you recall, in part 9 of my series, What Your Ignorant Teachers Could Not Tell You, I began discussing Radix systems and how they came about. And in this video, I'll continue where I left off in that video. So let's begin. Now, you'll recall that I showed you Radix systems are just a way of communicating in a systematic way. And I also showed you that they were invented so that we didn't have to learn much about the theory of fractions. In fact, we don't really have to know anything about fractions, and we can do all the arithmetic operations without any problems. Okay, so, and I showed you the main characteristics of a Radix system, that it does provide a unique representation for any rational number if its prime factors are contained in the radix. So for example, in base 10, to have a representation, the denominator of a fraction must only have two prime factors, that is 2 and 5. Any other rational number does not have a exact representation. In fact, it has no representation because the measure is the representation, and unless it is complete, then it cannot be a representation, because the fact that one obtains a repeating pattern is just a consequence of the knowledge that a rational number will not have the same prime factors. And obviously, if it cannot be represented in any Radix system, that's a consequence of the fact that it is not a number. That is, it is an incommensurable magnitude, which has no common measure with any other. In the mainstream, the idiot academics call such an incommensurable magnitude an irrational number, but it's not an irrational number, and there is a very remarkable difference between a magnitude and a number. A magnitude is not a number, it's just the idea of size or dimension, okay? So, and then I showed you some examples in the video. So let's just look over here and see. I talked about Simon Steven and how he wrote a book on tenths. And in this video, I'm going to continue to talk about infinite, so-called infinite decimal representations. Now, an infinite decimal representation does not exist. It is a myth. Okay, so for example, if we try to measure 1/3 in base 10, it can't be measured, all right? So if we write down 3/10, that is still less than 1/3, right? Okay, because if we convert both of these into quantities that we can compare, then we're going to have 9/30 is less than 10/30. Yes? Okay? So, and similarly, if we add another 300, so if we say, okay, well, maybe it's 3/10 plus 300, which is the same as 33 over 100. Well, that's still less than 1/3, okay? And the way we can work this out is we, again, multiply both the top and the bottom by 3, so in this case, you will have 99 over 300, and in this case here we'll have 100 over 300. So as you can see, it's impossible to measure 1/3 using tenths, right? So now let me show you a method to to convert fractions, to convert rational numbers into a certain radix. So most of you haven't learned this method, but some of you may have known about it if you've watched my previous video. So if you have a half and you want to write it in base 10, then what you're looking for is a way to express this in terms of the radix system, which takes this format, right? So all you need to do is just write down the particular digits, or some digit from 0 through 9, okay? If it was base 5, it would be some digit from 0 to from 0 to 4. If it was base 6, it would be one from base 0 to 5, right? So let's see now how to convert this into base 10. So it'll be the same as a half multiplied by 10 over 10, and that is the same as 10 over 2 multiplied by 1 over 10, right? Which gives us 5 times 1 over 10. And since there's nothing left over, we're done. And we can simply go ahead and write down a half as 5, okay, like that. And of course, if we don't carry this template around us, that's where 0 comes in, because it's pretty useful to remove ambiguity, and we can just write 0.5. Now, you'll have some infinitely stupid morons in mainstream academia who will tell you that something like this means the 9s are all there. That's absolute hogwash, okay? Now, if you just have a template like you have over here, you can easily assume that all the positions in the template, are blank, okay? But you can never assume that all the positions are of a particular kind of digit or a mix of digits, all right? That's just not possible. So, this idea here, this whole concept here is nonsense. There is no way that you can have all the 9s there, or all the digits of pi, okay, or all the digits of e, etc. That's just nonsense, because you don't know what they are, okay? And you can say, oh yeah, in this case, yeah, you know they're all 9s. Nope, you don't, because nothing goes on forever. Remember, the difference between 0.999 ... and 0.000 ... is that you can actually form the sum. The sum here is a super task. You cannot determine the sum. Well, you just try, for example, adding 9/10 plus 9/100, etc., and you'll see that the sum changes all the time. But if you add 0/10 plus 0/100 plus 0/1000, it's always 0. So this is really, in fact, the only so-called infinite sum. But it's not really an infinite sum either, because a super task cannot be accomplished, okay? So these are several misconceptions in the mainstream. And mathematics professors are highly stupid creatures who don't understand these things. Typically, they will brainwash their students by telling them things like, in the real numbers, we have this. But if you're not talking about the real numbers in a very arrogant tone, then blah, blah, blah. Okay, so, they'll use expressions such as, it is clear that. No, nothing is clear. Those are hand-waving arguments, all right? So now what I've shown you here is a method. I'll show you one more example, okay? So let's look at the representation, let's say, of 2/5 in base 10, okay? So again, we multiply by 10 over 10, right? And that becomes 20 over 5 times 1 over 10, which is the same as 4 times 1 over 10. In other words, 2/5 is 0.4, right? And that makes sense, because that's 4 over 10. And if we cancel this out, we're going to get 2/5, right? Okay, so now, and of course, if you had something like a quarter, it would be a slightly longer process because it would be 10/4 times 1/10, right? Which is the same as 2 plus a half times 1/10, right? Which is the same as 2 times 1/10 plus a half times 10/100. I just multiplied this by 10/10, which is the same as 2 times 1/100 plus 10/2 times 1/10 to 10 squared, which is 100, which is the same as 2 times 1/100 plus 5 times 1/10 squared. In other words, 1/4 in base 10 is fully measured. It is 2/100 plus 2/10 plus 5. This is wrong here. This is 10. Okay. 2/10 plus 5/100, which is the same as 25/100 or 0.25, right? Okay, so now let's look at an example where we convert to a base other than 10, okay? So how about this example? Let's take a quarter in base 7, okay? So quarter in base 7, we do the same process, and that's going to be 7/4 times 1/7, which is the same as 1 plus 3/4 times 1/7, which is the same as 1 times 1/7 plus 3/4 times 7/49. I just multiplied this by 7/7, and that will give us 1 times 1/7 plus 21/4 times 1/49, which is the same as 1 times 1/7 plus, and again here we're going to have 5 plus 1/4, 5 plus 1/4 times 1/49, okay? And that's going to give us 1 times 1/7 plus 5 times 1/7 squared, which is 49, plus 1/4 times 7/7 cubed, or 343, right? Okay, and of course you can see now that this pattern will repeat, because obviously we cannot measure a quarter in base 7, all right? No way to do that, because the prime factors of 4 are 2, and 2 is not a prime factor of 7. So we can see roughly here that a quarter is approximately measured as 0.15, and again, this whole process will repeat. Okay, so it will be 1.5, 1.5, ... And this isn't infinite, by the way. You can't measure a quarter in base 7. However, this here does have a limit, which is 1/4, okay? So let's check how that works. So let's clear this out here, right? So now we just discovered that 1/4 is approximately equal to, in base 7, 0.15, like that, okay? And of course, it's exactly equal to 0.25 in base 10, or 0.1 in base 4, or in base 8, what is it going to be in base 8? 0.5, right? Nope. Is that right? 5/8, I'm sorry. Let's see. What is it in base 8? 0.2. I'm sorry, 0.2 in base 8. Okay. So at any rate, we can actually see that the limit of this sequence here is indeed a quarter, but it cannot be summed, okay? There is no such thing as an infinite sum. And I'll get to that in a moment, but let's check this here. So we know from the the definition or the formula which gives us a sum to n terms, like that, gives us a sum to n terms, that if we break this up, like so, over 1 over r, 1 minus r, we know that as n becomes indefinitely big, then this tends to become very small, so that we can never reach this limit here, okay? This is the limit. And so typically when mainstream morons write sum to infinity is a over 1 minus r, it's really a limit, it's not a sum, okay? You cannot sum an infinite amount of terms. You cannot produce this sum. Look, this is the sum that you'd be trying to determine. In this case, yeah, 1 over 7, oh, sorry, not 1 over 7 squared, 1 over 7. Let's write it out first. It's 1 over 7 plus 5 over 7 squared plus 1 over 7 cubed plus 1 plus 5 over 7 to the 4, etc. Okay, so you could essentially break this down into two series, geometric series, as follows. Take this series, the sum of this series, and the sum of, it's not the sum, it's the limit of that series rather, and the limit of this series. Okay, now using this result here, we can say, the limit of the series, not the sum, the limit is going to be 1/7 over 1 minus the common ratio, which is 1 over 49, right? And that will give us 1 over 7 all over 48 over 49, which, by the way, is the same as what? 7 over 48, right? So we have this series here equal to 748. And if you work this out here, you'll reach the result, or obtain the result, that it's equal to 5 over 48. And so 7 over 48 plus 5 over 48 will give you what? 12 over 48, right? And that reduces to 1/4, okay? So you can see now that while this all makes sense in terms of limits, it makes no sense to actually call the sum of the series, or to define a series such as this series here equal to 1/4. That's wrong. The limit of the series is 1/4. The limit of the sum, okay, of the partial sum. So if you start adding the partial sums up like that, then the limit will be 1/4. But you cannot measure 1/4 in base 7, okay? 1/4 in base 7 is indeterminate. It's approximately 0.15, and as you add more of these on, it gets closer and closer to 1/4, but never reaches 1/4, okay? So this series here will always be less, the partial sum of this series here will always be less than 1/4. And since there is no such thing as infinity, the bullshit of infinity, you cannot sum that series up to say that it's equal to 1/4. And it's from these bad ideas of Euler, that Swiss mathematician, that you got this type of fallacy, 0.999 equals to 1. This here is total rubbish, okay? It's not true. 0.999 is not even a number. It's shorthand for the sequence, or the series, 9/10 plus 9/100 plus 9,000, etc. Okay, so I think I've covered quite a bit in this video, and I just wanted to show you a little bit more about infinite decimals. And in the next video, I'll try to wrap it up and show you that mainstream academics have 3 separate rules for numbers, what they think are numbers incorrectly, what their misguided logic leads them to believe are numbers. and they believe that these three rules, and they don't see them as three rules, they see them basically as the Euler declaration or decree, which says S is equal to lim S. But this is problematic because, as you've seen in previous videos, it doesn't work unless you have rational numbers. And even then, it can fail, for example, in the case of the third. So it's all messed up. It's all flawed, and I'm going to explain that to you in the next video, hopefully soon. Very well. This is the new calculus channel. I'm the great John Gabriel, the first. I'm the discoverer of the first and only rigorous formulation of calculus in human history. More advanced alien civilizations may already know of it. In fact, they probably do. Till next time, goodbye.